For those of you who are ECE students, you'll recognize me, except for the face mask. For those of you who are not ECE students, I'm Michael Gard. I'm professor of professional practice in electrical and computer engineering. The presentation we're doing today is intended primarily for ECE students because they have a syllabus requirement that there will be a refresher course about electrical safety topics at the beginning of the semester. And they're also required to have a 100% score on the quiz that will follow. So ECE students pay particular attention, although you've seen it before. And those of you who are not ECE students, it's probably worth your while to listen. For one thing, I believe that would be a quiz for you also, but the threshold is maybe lower. But the other thing is too, it's really not unreasonable to expect that at some point in your life you'll need to get behind an electrical panel in a house. And so this will help you. It will help keep everybody safe. So let's go ahead and get started. As I mentioned, it's required for engineering students. ECE syllabus number would be 4024. And if you're an ECE student, you need 100% to pass. What we're going to cover today is really nothing more than 120 volt domestic wall power. If you're going to do any other sort of a project source, that will require specialized training anyway. So if for example, if you're going to be using high voltage three-phase networks, this briefing won't do it for you. On the other hand, almost all the wall outlets in Endeavor are going to be the same as a domestic power panel or a domestic power outlet in your home or apartment. And so this is a perfectly acceptable way to tell you what to expect and how to keep yourself safe. Any kind of new material, any kind of new work, an electrician would call it, will have two different types of receptacles. These are called duplex receptacles because, as you can see, there are two of them. The thing I'd like to draw to your particular attention is that of these devices, these two blades here, if you will notice, they are not the same size. This one on the right-hand side, the way you're looking at it, is a little bit shorter than the one over here on the left, and that's no accident. That is because that for a 15 amp duplex receptacle, we almost always will want the neutral connection to be bigger than the hot connection. The other one that you see down here, this little thing that looks like a mouth, that's the ground connection. Now in some cases, we don't have a 15 amp receptacle, but rather one for 20. And the arrangement is exactly the same. We have a hot connection over here, the ground here, but if you'll notice, you have a T-shaped object here for the neutral. The reason for that is that if you have a 15 amp power cord, it will plug into a 20 amp receptacle and everything will be fine. On the other hand, if you have a device that requires 20 amperes, you cannot plug it into a 15 amp rated outlet. So it's a safety device, completely passive thing. But the idea is so that you won't overload the branch circuit. In all other respects, everything between the two is the same. So you have here 15 amps as a straight blade, and over here you have a T-shaped neutral for a 20 amp duplex receptacle. Now, as you might expect, it makes a difference what you plug into it or how you hook it up. And so the conventional nomenclature for a device like this, and we'll use a 20 amp receptacle because that way you're clear about what the neutral is. There are three types of connections. You have your hot wire, and that goes to a part of the connector that's made out of brass, kind of a coppery color. So that's your hot connection. That's the one that goes to the circuit breaker in your circuit panel. On the neutral side, over here, those connections have a silver colored screw for their electrical connections. And that's the easy way to remember that is, as you'll see in a moment, almost always the neutral is white. So the white wire typically goes to the silvery colored thing over here. But more important than that, if you're looking at the face of the thing, you should be able to tell it's the neutral because it's either shaped like a T or at the very least, it's the longer of the two. Down in here, we have what's called the ground. Typically, this might even be painted a kind of a green color on the screw where you make the attachment. The ground connection goes to the little metal frame that supports the receptacle body, and that in turn is connected to the internals of the power outlet box. Sometimes there's a conduit ground, mostly there is in new construction. And so it's a safety connection, and we'll talk about its requirements here in just a little bit. But this is standard nomenclature for a typical domestic panel. It's a single phase device, so you don't have to worry about which phase is which. It's a single phase device. You have a hot, which goes to the breaker. You have a neutral, which goes to a breaker bus. You'll see that in a moment. And then you also have a ground connection, which is actually a safety connection. Let's take a look at the appearance of these things. Notice that this is a 20 amp receptacle, right? Because we have the can we back up a little bit?
Yeah, that's no problem.
I'm sorry.
Nope. I can cut it out and then we'll continue.
Okay.
Ready to go.
Okay, thank you. Okay, so what we're looking at now is a photograph of a receptacle face. It's a 20 ampere receptacle, as you can tell, because we have the T-shaped structure over here. So again, this is the neutral, this is the hot, and these are the grounds. Think of it like a little face. If it's winking at you, the short one is the hot line, the bigger one is the neutral, this is its little mouth. If you take a look at the back of the receptacle, and this is the same device, and it was one that was pulled from service, because they do get a little grungy. You're looking at the back, and down here I want you to notice that here is a screw. That's for the ground connection. That ground connection is established to the little piece of metal here, which is actually an extension of this entire back strap. And then these little wings up in here where they attach into the electrical box. Everything that you see there that's aluminum or steel colored or tin colored if you prefer, that's a grounding connection. So that's the back of the receptacle. Let's take a look at the side connections, because if you're inside an electrical panel, this is what you're going to be interested in. On the neutral side, here we have the neutral receptacle bus bar. Notice that this is silver, and these things just connect up. Most of them are arranged where you can either poke the wire into a small hole and there's a keeper mechanism, or depending on what you need to do with it, you can also twist or actually make a hook out of your connecting copper and put it under the screw. What we're showing over here is the receptacle's hot side. Notice that the orientation is the same, even though the view is slightly different, because now we're looking at the connections to these little shorter pegs. Notice that this is now brass colored. It may not show up particularly well when you watch the video, but this is the brass colored connection. And if we take a look at the receptacle body itself, here's that screw that we saw ahead of time. It still has a little faint patina of green, but you'll notice that this body right in here, all of this is a single piece electrical. So that's the anatomy of a typical domestic 120 volt receptacle. And that's that's going to be typical of the devices that you encounter in Endeavor and in any of your other lab areas. Sometimes these are installed upside down with the round pin up on top. Everything's fine. The orientation remains the same inside the receptacle body. Now, as we mentioned, that's the anatomy of the receptacle body. But let's talk about what's behind the receptacle. We're going to take a look at what constitutes a typical domestic power panel. And we're going to talk about the insulation color codes that are most commonly encountered. And then we'll kind of build up the anatomy, if you'd like, of the electrical connections in the panel. The typical color conventions for installations in an electrical installation in a dwelling or an apartment, whether it's a receptacle or a plug cable, the hot wire is typically black or red. Neutral line is typically white. And then the ground, it may be a green wire, it may be bare copper, and depending, it's sometimes mostly in a cord set. In other words, the cord set is the plug that has a pigtail off of it, and sometimes those can be green with a yellow stripe. But in general, black or red, that's going to be the hot wire. White is going to be the neutral. And then you'll have either a green insulated wire, a bare copper wire, or maybe green with yellow stripe. And that'll be your ground. The ground can be thought of as a safety connection. If you're dealing with European standards, or some purchased cord sets, especially if they have an overseas relative to the U.S. source, sometimes their color conventions are a little different. But if you're looking at a conventional U.S. domestic power panel in your garage, or in the breaker panel in your apartment, this is probably what you'll see. Those of you who are familiar with Romex cable, which is widely used when people do their electrical wiring in new construction, it's got a jacket with a black wire, a white wire, and a green wire. Or it's got black, white, and maybe bare copper, but that's pretty standard. But red is an acceptable hobby as well. Let's take a look at this. In the typical domestic power panel, what you think of as the connection from the pole is actually the primary side of the transformer. So this is the thing that's in the air, and you don't really see it by your house as a rule. What you do see at the house is the secondary side of a transformer that's center tapped. And this is usually what's called the service entrance. More often than not, this contraption right up in here is mounted on a pole or maybe on a pad close to where you live. And the connections that you see are the ones that actually go into the house. So you'll have two phase lines, they're called, and then a center tap. The center tap is actually your neutral. And furthermore, when you go into your electrical panel, that neutral is a special copper bus. The bus bar itself is basically a long rectangular piece of copper that probably tin coated, that has tapped holes in it for screws and such. And that's where you make your electrical and ground connections. There's also a large conductor which is actually buried in the ground near the surface panel, near the service panel. And that's what's called the earth connection. And that is really true. It really does go into the soil. So that's your service entrance right up in here. Next thing that you encounter, typically at the top of the breaker bus, or the breaker panel, is a main breaker. And if you'll notice, those are ganged together. So if you trip that out and open them up, then you usually disable both sides of the bus, both phases. So this operates as a single unit, but it controls two different phases. Remember, we have two different phases coming off of the transformer. One side is called arbitrarily your phase A bus. The other side is arbitrarily called your phase B bus, measured with respect to neutral. In other words, this side, with respect to the center tap, is nominally 120 volts AC. Your other phase line, measured with respect to the neutral, is also 120 volts AC. Across the two of them, it's 240. So when you have power to your electric range or to an electric water heater, those typically, because their loads are heavy, they typically span between both buses. But for normal operations, lights, typical plug-in appliances, typical portable loads, we need 120 volt power, and those can be connected either to the phase A bus or the phase B bus. It doesn't really matter which, because it'll look the same. The way that things operate from that, you have your individual circuit breakers. Typically, these are single pole devices unless it's a very heavy load. So if, for example, you have a load in your living room, you have lights, you have convenience outlets, have a stereo plugged in, those sorts of things. That's typically on a single powered line, and it has its own circuit breaker back in the breaker panel. All of those devices in your living room are then connected through that breaker to the hot connection on your receptacles. Notice too that the neutral goes back to the neutral bus. It is not switched. It should never be switched. It goes back to the neutral bus. And notice also that the ground connection actually returns to the same bus as your neutral. So it's actually neutral and grounding bus, which ultimately is connected over here to Earth. That's a safety device. It's a safety convention. And when we talk about ground fault circuit interrupters, you'll see why it is the way it is. In terms of the lab, that's pretty much a conventional domestic panel. And as we mentioned in the lab, it's pretty much the same thing. So enough of the anatomy, what's behind the wall. Let's talk about how we use it. AC power in the lab, 120 volts. You have to respect it. It may not kill you, but it'll hurt. And so there are some conventional rules that are necessary for you to follow to work safely. Do not, I repeat, do not work on energized equipment. If you have to dig around into something that's line connected, disconnect it from the outlet first. Make sure that you see that power cord laying there in front of you. Open and lock out the breaker when it's possible to do that. If you're doing work on something, disconnect it if you can, but otherwise open the breaker and lock it out. You may remember that Mr. Hogan last semester gave you an electrical safety briefing about lockout tagout. This is where it matters. And then after you have worked on something that's a line powered device, be sure to confirm all the voltages in the circuit when you turn power back on. Confirm all voltages that are the power connection using a voltmeter to make sure it's really doing what you want it to do. It's a good idea just to flip the power switch if it has one. And again, you confirm its operation by using a voltmeter. I strongly encourage you to remove rings and any other jewelry in the laboratory. This includes things like necklaces, it includes earrings, it includes simple pins that might be hanging off an article of clothing. Those things are conductors, and if they come across a power connection, they will conduct just fine. Rings especially can sneak up on you because they are a closed loop And if you're dealing with high frequency magnetic circuits, they act like a short circuited term. So you can actually damage your finger by heat if you have a ring that's close to a rapidly alternating magnetic field source that's intense enough. So if you can, remove the rings, remove all the jewelry, keep yourself safe. And what I do when I have to measure stuff inside the power connection, I use an alligator clip for the ground or for the low side of the measurement. I hold the probe for the hot lead in one hand and I put my other hand in the pocket. If you don't touch it to anything metallic, you're going to be fine. So I encourage you to follow those rules. Breakers, switches, other equipment in the power system, it is possible, it happens, that those can be wired incorrectly. Take nothing for granted. Check it for yourself. I had a friend who was helping an old farmer somewhere in Ohio. This is where they had hand-dug wells. It was fairly shallow. And this old farmer had a sump pump, basically. What it is, a submersible pump in a water well, and the pump had malfunctioned. He asked my friend to help him because he was getting along in years. My friend said, well, okay, is the breaker open? And the guy said, yeah, breaker's open. But my friend thought about it for a while and he said, you know what, I'm going to double check. And so he did. Took a voltmeter, went up to the pump leads, and what he found was that even though the breaker was open, there was 120 volts on the pump leads because somebody had wired the breaker incorrectly and put it on the neutral side. So if he had gone down into the water and picked up that pump to work on it, he'd have been dead. Don't take it for granted. Check it for yourself because it only takes one mistake to have a really serious consequence. So check it out yourself. And ask for help. Take no risks. Don't assume anything. Ask for help if you need it. No horseplay in the lab. No practical jokes in the lab. The lab's serious business and people can get hurt. We don't want that. So those are the rules for using AC power in the lab. If you were here in person, I'd be asking for questions right now. Keep yourself safe. One other item that's particularly important, and this is for the ECD students in particular, but everybody should know this. How do we specify power? Because you hear it a lot of different ways. Well, people, when they talk about it, they'll talk about the amplitude of the sine wave, mathematically, for example. They'll talk about the peak-to-peak voltage. You hear about that. And then there's also what's called the RMS voltage. And that, when people talk about volts AC, typically what they mean is the RMS voltage. But let's take a look at a little cartoon that shows us what these things look like. What we have here is a sine wave. Mathematically, it would be 170 sine 2 pi ft, typical sine wave. And in this particular illustration, the amplitude is 170 volts, right? Amplitude is being this part, and then the sinusoid reverses. But it's a sine wave, 170 volts peak. So 170 volts peak, if we take a look at it, we have a period in domestic power. This is 60 hertz, so it would be about 16.67 milliseconds. But this is also what would be called 120 volts AC, or 120 volts RMS. We'll go into the math here in just a moment, but notice that if it's a mathematical description, the same signal is 170 sine 2 pi ft, but it actually has 340 volts peak to peak, and it's also known as 120 120 volts RMS, or AC, volts AC. And here's why. When you're comparing power, the folks who originally did this work would like a way to relate power produced by an AC waveform to DC power, like from a large battery. And so ECE students should remember this, but so that you can impress your friends and neighbors, here's where the name comes from. If you'll notice, we have the amplitude of the signal, A sine 2 pi ft. That's the mathematical description of the sinusoid. And we square this. Okay, so we now have A sine 2 pi ft squared. Then what we do is we want to find the average of that signal. And the way we do that is we integrate it over a full period and then divide it by the period. That's called the mean, right? Then what we do is we take the square root. So what we have, working from left to right, is the root of the mean of the square of the waveform. And it turns out that is an equivalent amount of power as you would get if you put 120 volts DC on a resistor. So 120 volts DC on a particular resistor produces a certain amount of heat. And 170 volt 170 volt peak amplitude sine wave, if it's a pure sine wave connected to the same resistor, will produce the same amount of heat. So it's a convenient way to relate DC power and AC power. That's where the name comes from, but notice that we describe things in 3 different ways. So we have, just to remind you, 170 volt sine 2 pi ft has amplitude 170 mathematically. 340 volts peak to peak is just as good, and if you're specifying component tolerances, you need to know that. And then the other thing is that actually is 120 volts RMS. Those are good numbers to remember. They frequently occur on quizzes, like about 100% of the time. So, just to let you know. And finally, well, we're talking here about amplitudes. We've just gone through this. For the domestic distribution line voltage, nominally 120 volts AC. 120 volt AC is really 120 RMS, which is a root mean square voltage and an assumed sinusoid. Nominal, by the way, means in name only. In reality, the AC power line can be, at any given time, probably somewhere between 105 volts AC to 125 volts AC. Depends on the load. So 120 volts is nominal. We talked about this again. 120 volts RMS is 170 sine 2 pi ft volts. There's 340 volts peak to peak. And when you're specifying things, you need to know the difference. Okay, and last topic, and this will be new material, and so at least for this semester, it's not on the quiz for the 4024 group, ECN 4024. We also have ground fault circuit interrupters. In normal operation, the hot and the neutral conductors to a load have to carry the same current. Mr. Kirchhoff says that what goes in comes out, and that's what this means. So if everything is connected and operating properly, if your hot lead is carrying 3 amperes, then your neutral should be carrying 3 amperes. The ground should not carry any current. It's all between hot and neutral. If the hot and neutral currents aren't the same, well, the current has to be going somewhere. We don't know where maybe, but we know that it's not behaving the way it should. And this situation is called a ground fault. So the missing currents, assuming is assumed to go to ground somehow, somewhere. We don't know, but we do know that there's an imbalance, and that's usually a dangerous situation. The National Electric Code mandates the use of ground fault circuit interrupters as a protection device in specific locations, particularly within 6 feet of water. For example, kitchens, bathrooms are good examples. But they're useful in different parts of the house, but that's especially where they're used. You'll probably see them there if you see them anywhere. And the question comes up sometimes, what current difference is required to make it trip? In other words, how large a fault constitutes a ground fault? And the most common is Class A GFCI, and that should trip at about 5 milliamperes. Pools are allowed a little bit more leeway at 20, but for the most part, you'll be dealing with a ground fault circuit interrupter that's a Class A device. What do they look like? Well, in this case, this is a shot taken right off of by the sink in the bathroom. Notice that it's the same face, hot lead, longer neutral, ground. The difference is here is that you have 2 little buttons, one of which is labeled test, which is just there to make sure that the device is working. Push the test button, it should pop off, it should trip. And then the other one is a reset. So you have a way to check it. Now that's meant for permanent installations. Some things like hair dryers, for example, and this is one such plug, they have a built-in GFCI connection. So what we're looking at here is a device that's meant to operate, and it's double insulated is one other requirement. Notice that we have this little thing down here that's wider than this one. This down in here is the neutral. This is the hot lead. And if you take a look at the other side of it, what you'll see is that you have a ground fault circuit interrupter built into the cable itself that also has a test button and a reset button. And it's not uncommon to have these things when you first plug them in trip. So probably a lot of you have had that experience. Well, that's it. I wish I could have given this to you in person. But I encourage you all, work safely, work carefully. For those of you especially who are ECEM students, be sure to remember these definitions of the power waveform. And with that, I wish you a very successful fall semester, and good luck to you. Thank you.